Hello everyone, thank you for coming. Today we're going to talk about static control flow in C++14 and how to implement it. Everything you're going to see is already available in this GitHub repository. So let's begin by having a very brief overview of the talk. So we're going to begin by defining static control flow. What do I mean by static? Then we're going to take a look at the history of static if in C++. We're going to take a look at if-const-expr, which is a new thing in C++17, and we're going to look how to implement our own static if in C++14. And all of this will be done with slides. Then we have static if implementation details and compile time iteration, and all of that will be done with code and comments. So there's going to be a lot of code. Hope you're ready. So what is static control flow? In C++, static is a specifier that has multiple meanings. It's also a word that many developers commonly use to define compile time control flow. For example, languages such as D have constructs called static if, which allow you to branch upon a compile time condition. So the goals of this talk will be understanding the benefits of static control flow, looking at the history of this kind of flow in C++, and implement our own compile time branching and compile time iteration constructs. So let's start with an example of another language. Let's look at D. This is an example of static if in D. And as you can see, it looks very weird. You're defining the same alias in two different scopes with the same name. So what's actually happening here, this is more like a preprocessor if-def. It has a compile time condition, and depending on whether the condition is true or false, it's going to define the alias with a specific type. So as you can see, the compiler almost completely ignores the branch that's not taken, depending on the predicate you pass. So how would you do this in C++? Anyone? Macros? No, I don't like that answer. Exactly, yeah. I heard some explicit specialization, and this is what you do in C++. You basically define a template class or struct, and then with specializations, you define your alias. So as you can see, there is a very different philosophical approach here. D allows you to ignore the scoping rules, while C++ still only wants you to define a single thing in a specific scope. So let's go to C++ now. This is an example of a variadic template function where you have the current argument and the rest of the arguments. And this is one of the methods you can use to handle a variadic pack. So basically, you have a base case, which handles a single argument. And then you have a recursive case, which calls the base case. And if the argument tail is not empty, it will recurse and basically call a function on every element. This is OK. The problem is that we are splitting the logic of handling one argument from the recursion logic, and we have to define two overloads, and that's considerable code repetition. So what if we had some sort of magic construct that allowed us to branch at compile time given a constant expression? Turns out we have something in C++17 that's called if-const-expr. We can simply pass a constant expression as part of the predicate, and the branch will only be instantiated at compile time if the condition matches. So in this case, this will not give you a compilation error if the parameters pack is empty, because the condition will be false and the branch will not be instantiated. So this is C++17's answer to the desire of developers to have static control flow. As you can see, the benefit here is that the code is local, and we have no code repetition, and it's easier to reason about this function because you don't have to jump around in the source code. Another example is constructing object with the curly brace syntax and the parenthesis syntax. One way you can do this is using enable if. This is an example where you are specializing make unique depending on whether or not you can construct the object stored in the smart pointer with the curly brace syntax. So you're just using enable if with a predicate, and if the predicate evaluates to true, then you call the parenthesis construction syntax, otherwise you call the brace construction syntax. As you can see, this should just be a compile time if. We have a lot of boilerplate caused by enable if. We have two overloads when the function is actually doing the same thing, and yeah, it's harder to reason about, harder to maintain. So we have our magic compile time if. we pass it a constant expression condition, and the compiler is going to instantiate only the branch that matches the condition. Again, it's way cleaner. You don't have enable if stuff. It's local. It's a single function. You don't have code repetition. And I think it's pretty cool. This is part of C++17. It got accepted. And we'll take a look at the history of static if in C++. So the previous examples were taken from this proposal here by Bill Vutilainen. I'm sorry if the pronunciation is wrong. And the paper is a resurrection of two very controversial static if proposals, which were in 2011 and 2012. And the first one was by Walter Brown, and the other one was by Walter Bright, that went on to develop the D language, Herb Sutter, and Alexandrescu. So the original static if proposal was very controversial because it had similar ideas to what D is doing today. It didn't respect the normal scope rules you expect from C++, and it almost literally had the compiler ignore the branch that was not taken. So you could write code that was not valid C++ in terms of syntax. So these two above proposals were actually considered harmful in another proposal by Bjarne, Gabriel Reis, and Andrew Sutton because of the unintuitive scope rules and inconsistency with the rest of the language. So we didn't get any of that. Fortunately, in 2015, Bill resurrected static if, giving it the name if_constexpr, and making it follow the usual rules we're all using today in modern runtime code. So starting with these proposals from 2015, the idea of a static if began to gain traction, and it was refined multiple times in 2016, and finally in Ulu, in the standard meaning at Ulu, it was accepted for C++17. And I'm very happy to say that we finally have this construct into the language. So this is the example from before, and that if_constexpr is actually part of the language. It's not magic. It's not pseudocode. You can write this in GCC 7 and in Clang 4.0 right now, so if you want to play around with it. And the point is that even if the code inside the branch is not valid, it will compile as long as it has a valid C++ syntax. So it has to be parsable, but it doesn't have to be valid in the context. It only depends on the constant condition. And again, this is the same example as before, and it's valid in C++17. The rules to follow are that if_constexpr is restricted to block scopes. It's always going to establish a new scope, and it requires that there exists values of the condition so that either condition branch is well formed. So what does it mean? It basically means that only the matched branch will be instantiated, and as long as all the other branches are parsable, it doesn't matter whether or not they are valid in the current context. So remember this thing from D? No, forget it. We can't have that. We're going to follow the usual C++ rules. You can obviously chain branching with if_constexpr. You can just say else if_constexpr, and all of this will be evaluated at compile time. The problem is that C++17 compilers are currently experimental. GCC 7 is only in trunk SVN, and Clang 4.0 is still in SVN as well. So you don't have to wait until C++17 is supported by your architecture. If you have a support for C++14, you can actually implement your own C++14 static if version. That's what we're going to explore today. So before we dive into the implementation, I'm going to show you a simple example. Let's have this ridiculous situation where we have multiple food-related classes that have slightly different interfaces. So we have banana and peanuts that we can eat, and we have water and juice that we can drink. And our goal is to create a generic consume function that accepts any kind of food and prints something to std out. The way we can do it is by having a template variable that categorizes the class, sort of like a concept that we're manually satisfying by specifying the classes that match it. And we are categorizing the solid foods on the left and the liquid foods on the right. And this is important. The predicates are constexpr, so they are constant expressions, and they can be used to branch a compile time with if_constexpr or with static if. And this is what we get out of it. It's obviously not as pretty as the C++17 version, but it is equivalent in semantics and behavior. So we say static if or condition, which has to be wrapped into bool v to force a compile time evaluation. And then we chain methods using this kind of then syntax, else if, then, else. And you can think of this as a set of lambdas where only the lambda that matches the predicate will be chosen and instantiated. All the other lambdas will never be instantiated, but they only have to be parsable. So again, bool v is required because we need to force the condition to be a compile time constant expression. And bool v is something like this. If you've used Boost HANA, you should be familiar with this kind of type value encoding paradigm. And what we're doing is basically defining a compile time Boolean type, which is just integral constant of bool, and a template variable to avoid instantiating it every time. So as I said, this kind of idea of wrapping types into values and values into types is what makes libraries such as Boost HANA or Fit and Tick extremely powerful and still have a very nice runtime-like syntax. You can read more about it in these links. So what's happening here? We have these branches, and the scope rules are what you would expect. As these are just regular lambdas, there is no escaping of naming, so there's no way you can implement something as static if in D. And you have to think as every branch of the static if as a template function that will only be instantiated if the predicate matches. So in this example, even if y, the method each of y does not exist, we won't get a compilation error because the branch won't be instantiated. So as you can see, you can try calling methods that do not exist on the current object as long as, as the code inside the lambda is valid C++ syntax. This pattern can work thanks to C++ 14's generic lambdas. In fact, when you write something like this, which is a C++ 14 generic lambda, the compiler evaluates it to something like this. It's basically syntactical sugar for a local struct that, as an anonymous type, it has a templated operator call that, in this case, takes a forwarding reference and then executes the body that you pass in the lambda. So for all intents and purposes, the compiler sees the lambda with the struct. And the important thing is that this struct is actually a template. Sorry, the operator of this struct is actually a template. So what allows static if branches to be instantiated only if the condition is true? The idea is that we're passing back the argument at the end of the static if in order to delay the instantiation of the template until we have found a matching branch. So as you can see this, we're forwarding x back into the static if, and then it's going to find the branch that we want to instantiate and instantiate it with the x that we're passing to it. And this is used to delay the instantiation of the branch that matches the compile time condition. So if this is not clear, let's analyze the technique step by step. So the first step is just calling consume. And in this example, we're just passing a juice variable, which, if you remember, is drinkable but not solid. Then the second step is finding the matching branch. So we're going to take a look at the condition, evaluate it, and go over every single condition until we find one that matches our current object. As soon as we find it, we know what branch we want to instantiate. We will ignore all the other branches. Then we instantiate and call the matching branch. And this is basically what happens. By ignoring all the other branches, only the body of the lambda and the call operator remains, and you just stick those together, and you're actually instantiating that specific lambda, ignoring all the other ones. So you have to imagine that the entire static if collapses to the first matching lambda's body, and the remaining call syntax is calling the body that the entire construct collapsed to. So in this case, x is getting passed back into the static if. That thing is going to get called, the lambda is going to get called with that thing, and this is what happens in the end. So you're just instantiating that specific lambda, skipping over the others. So another question for you guys. Would capturing the lambda, the variable in the lambda, work? Instead of passing back the variable, we're actually capturing it. What do you think? Why not? You said no, now you have to explain. Okay, so the answer is it won't work because it's not a template, and that's exactly the problem. If you're capturing the variable, what the compiler will generate is something like that, where we still have a type-deduced operator call, but it's not a template anymore. So as soon as the compiler sees the body of the lambda, sees the lambda is trying to instantiate it, and it will obviously fail because juice does not have the eat method. So this will cause a compile time error even if the branch is parsable. Another way you could design this is instead of passing back the argument to the static if, you could just pass back a dummy argument which will just trigger the template instantiation. But it's just an implementation detail. So that's the end of the slides. So let's jump right into the code. As you can see, I'm going to compile and run all the code snippets here on the right. The first code snippet will show static if in action. So this is the example that you've seen in the slides. We have 4 different structs, which are banana and peanuts that have an eat method. Then we have water and juice that have a drink method. And then we define some predicates, his solid and his liquid, which are constexpr variable templates, which are specialized on banana and peanuts in order to mark them as solid, and for water and juice in order to mark them as liquid. Now that we've done all of this, we have the compile time knowledge to branch, and so we're gonna implement our consume function that takes a generic t instance by forwarding reference. And inside consume, we can use static if with our constant expression predicate. Then we have the syntax here that I've shown you, where we use .then continuation and the true branch here. And then we can compose our compile time branch by adding else if and subsequent then branches. And at the end, we have the catch-all else branch. As you can see, we're using generic lambdas here, and we have to pass back the argument which we receive from the user in the consume interface to the branch that was matched by the valid predicate. And that's done in order to avoid instantiating the non-taken branches. In the main, we're going to call consume with banana, water, peanuts, and juice, and also with 2 non allowed objects, such as an int and a float. And if we compile and run this code snippet over here, we can see that it prints heating solid, drinking liquid, eating solid, drinking liquid, cannot consume, which is what we expect, because the first 4 are valid, and they're going to alternate between solid and liquid. Then, since we don't have a predicate for int and float, both of these checks are going to be false. So the static if is going to go into the else branch at the end and print out cannot consume. So the code above would look something like this in C++ 17, thanks to the new if constexpr syntax. And as you can see, the logic is completely identical to the one above, but we don't have any boilerplate due to generic lambdas or passing back the argument. So this is very clean. We can just say if constexpr and use the same name for the variable inside the branch as the one that was passed by the user. In the second code segment, we're going to finally implement static if. And in order to do that, we first need to define some utility macros analysis. The first one is called FWD, and it's a variadic macro that wraps forward and avoids the repetition of the type inside the angle brackets, because it can be deduced by the pass argument. The second one is called bool underscore, and it represents a Boolean value as a compile time integral constant. And as you can see, it's simply an alias for a std integral constant of bool. In order to make it even nicer to use, we can create a variable template called bool underscore v that will allow us to not have to use the curly brace syntax at the end. So this is going to be an instantiation of the bool underscore type. Note that in C++ 17 we'll have bool constant, which is pretty much what this alias over here is doing. My static if implementation was inspired mainly by this article by Baptiste Wicht, which you can find on this link over here. And it's a comment on the Reddit thread. Also, there was an issue on the CVP core guidelines repository where they discussed this. And if I'm not mistaken, it was Paul Foltz II who gave some interesting examples about an static if implementation in C++14, which I used as inspiration for my own. The implementation will be composed of the following elements. We're going to have an interface static if function that returns an instance of some helper struct, and this helper struct will be called static if impl, and this is what will allow the user to do the then, else if, and else chaining, and eventually when the correct branch is matched, it will return a result struct. The result struct will be called static if result, and it will ignore all the chaining calls that might be still in the static if chain, and its job will be to execute the match branch. The interface function, as I said, will be called static if, and this is its signature. It will take some compile time predicate as its parameter, and it will return the helper struct. So we're passing t predicate as a parameter as a normal value parameter, even though it's a compile time boolean, because we want to be in line with the new type value encoding style, which improves the syntax and makes the gap between metaprogramming syntax and normal code syntax way smaller. Then we're gonna see the forward declaration of our implementation struct, which is called static if impl and will be returned by the interface function. And this struct will hold the result of the predicate as a template parameter. And when calling static if, we will return an impl, but as soon as we find a matching branch, and we find it when the predicate evaluates to true, then we have to return a different type, which is static if result, so that we can propagate it through the whole branching hierarchy and call the correct branch, which is a generic lambda function. And this is its signature, and it's just a struct that has a template parameter called tfunction to call, and this will be the type of the lambda that will be invoked if the branch predicate evaluates to true. So let's reiterate one more time. Static if impl will be returned by the static if interface, and every instance represents a branch. The type will be specialized depending on whether or not the predicate is matched. If you remember, we have a boolean template parameter here. And static if results instead will ignore all the subsequent chaining methods and will inherit from the branch lambda through this template parameter here in order to be callable. It will be returned by static if impl true if a 10 branch is matched, otherwise it will be returned by static if impl false if an else branch is matched. Now let's dive into the code and see what it looks like. And we'll start again by an additional layer of syntactic sugar, which is this make static if result function, which will help us by deducing the tf parameter, which will be the lambda type, which is stored here in the static if result. And then we're going to finally specialize static if impl for the true predicate evaluation and for the false one. In the case of the true evaluation, we will have to return a result when we match a then branch that has a true predicate. Otherwise, we have to ignore else and else if. And in order to achieve that, what we're going to do is gonna provide three methods which the user will be able to chain. And in the case of else and else if, we will return ourselves because we want to ignore what the function provided by the user inside this branch does, since our predicate was true. Instead, when we find a then call, what we're going to do is returning a static if result by forwarding the function inside the result struct, because this is the matching branch and we don't care about anything else. So we're going to return this result, and eventually this is going to be called by the last parameter in the chain. For the false specialization, we will do the exact opposite. We will ignore all the then chaining calls because the predicate is false, so we want to go down into the hierarchy of this chained method calls. And when we find an else that doesn't have any other condition, we will assume that it is at the end of all else if calls, and we will return a result and ignore everything else because we had a false predicate and we're looking for a branch that is valid, so it has to be an else or an else if. In the case of else if, we cannot ignore it, but we still have to do something. We cannot return a result because we still have to evaluate the predicate. So what we do is simply create a new static if with the predicate inside the else if and return that instead, so that we will continue this branching logic on a new static if instance. Another thing to take care of is the eventuality where the user provides only a static if without an else branch. In that case, if the predicate evaluates to false, we need to make our own static if helper implementation with this false specialization callable. Otherwise, we would try to call something that's not callable and cause a compiler error. The last piece we need to complete our static if implementation is static if result, which is pretty straightforward. What we do is inherit from this template parameter here, which is the type of the lambda or function that belongs to the specific branch. And this allows us to make use of the empty base optimization in the case that the size of this object is 0. And our constructor will take the callable object by forwarding reference and initialize the function to call parameter, which is our base class. And since we found a result, we want to ignore everything else. So then, else if, and else will all return ourselves so that we can propagate this branching up until the last parameter, which is the parameter that we use to call the match branch. And that will be done automatically for us because since we are inheriting from a callable object, we will expose the call operator right to the user. And finally, the last pieces are the implementation of the interface functions, which are pretty straightforward. They just help us deduce the template parameter for the classes and return an instance of them. So let's see some additional examples in the next code segment. So this first example is something that I really encountered while coding one of my libraries, VRM core, and I was trying to write a resizable generic buffer, and I had to detect when a type was movable or not because I was trying to keep count of them for a test. So what I did, I had this grow function here, and I was basically copying stuff from a buffer to the other, and I wanted to keep track of what I was moving, what I was copying. So to do that, I used static if inside the copying loop with the SED's move constructible t, which was the type of the elements I was copying. And in the case it was move constructible, I was incrementing this variable here for testing purposes and using SED move explicitly. Otherwise, I was incrementing this copies variable and just using the copy constructor. So as you can see, I didn't have to create an extra overload. I didn't have to use explicit template specialization. Everything is localized here inside the loop, which I think is way easier to understand and read. Another example is again from a true situation while I was working on my thesis project, ECST, which is a compile time entity component system library. And I required some sort of left fold at compile time over a list of types. And in order to implement the recursion without repeating the function twice and specifying all the complex no except operators and expressions 2 times, I simply had a single function called foldL step, which took a list of values, which are actually types wrapped into values. And in order to stop the recursion, I used static if over here, where I looked at the size of the parameter list, and if it was greater than 0, then I had my recursive case that called the lambda itself over and over. Otherwise, I just had my base case over here, which returned the accumulation value at the current step. Again, I think that this is way nicer to read than having 2 separate functions where you have to repeat the template parameters, an eventual no except specification, and name, and a lot of other stuff. And I find it easier to reason about because it's localized inside a single function. So branching in an almost imperative way at compile time is very useful. And I'd like to analyze another operation that we often do in imperative code, which is the for each loop. Let's see how we can implement something similar at compile time in the next code segment. So one possible starting point for a compile time for each loop is the famous for each argument snippet that was originally posted on Twitter by Sean Parent. I actually gave a talk about it at CPPCon 2015, which is called for each argument explained and expanded, and I go into detail about the snippet over there. And this is its implementation, a quick example. So as you can see, for args is a function that takes a callable object as its first argument, and then a set of values. And the idea is that we're going to call f with every single value inside the XS pack in order. To do that, we need some kind of context where variadic parameter expansion can take place. And one such context is std initializer list. And in this case, we're using int as the template parameter, but we can use whatever we want. Then we will open the curly braces of the initializer list to construct it. And inside we'll have this expression here, which is very weird. Basically, we have this comma operator here that makes the entire expression evaluate to an int, so that the compiler is happy by inputting it inside the constructor of its initializer list of int. And on the left-hand side of the comma operator, we have the function call of f, which is our callable object, and xs, which is our variadic pack of user-provided values. So what's going to happen here, thanks to this ellipsis operator, is that this expression enclosing round parentheses is going to be repeated for every argument inside xs. And since the expansion of an initializer list constructor where we have a variadic expression is guaranteed to be expanded from left to right, we will get our desired result. And that is that f will be called for each argument inside xs in order. I have an example here. So for this for each call, where the first argument is a lambda, generic lambda that basically calls stdc out on the past argument and then adds a space. And then we have some arguments here. This is roughly expanded to something like this. So we have our initializer list, we copy paste f in every call of the initializer list, but the argument we're going to call it with is different every time. We have a hello, 1, 2, and 3. And in every expression, we have the comma operator that makes it evaluate to an int, and everything is wrapped in round parentheses. So this is the same as writing this for the compiler. So we're literally just resolving this sequence of calls at compile time into something like this. And I think it's pretty cool because it allows us to avoid repeating the call, and we have a localized way of defining an operation over a set of heterogeneous values that are provided by the user without having to repeat code or to resort to runtime overhead. So for args will be implemented in a much cleaner and straightforward way in C++17 because we have something called fold expressions, and you can learn more about this feature on this CPP reference page. And what we're going to do is simply use the fold expression over the call operator of the function and over the comma operator. And basically this is going to be expanded exactly to what we did in for args. So f called on every single argument of xs in order from left to right. The next code segment will explore this knowledge about for args to implement compile time iteration. Let's start with a usage example of for args. So this is the implementation of the function without any comment or spacing. As you can see, it looks quite scary. Anyway, let's say we have a template buffer struct that takes a number of bytes as a template parameter, and we have some allocation on the allocation functions over here. And we would like to run some tests on this struct by using different amount of bytes. Imagine if the byte count was a runtime parameter, then we could do something similar to this, which is simply using a for loop over a list of integers and instantiating the buffer with the n value over here, allocation, performing the tests, and the allocation. Cool. We would like to write something like this for the compile time parameter as well. How do we do that? We can use for args as our stepping stone, and you need to remember what we did a few code snippets ago. We defined some helper type and context variable for booleans. Why do we do the same for size t or for an integer? Well, we can use this st underscore, which stands for size, which will be an alias for an integral constant of std size t, and its context variable template will be sc underscore v. And now what we did is we have created a wrapper for arbitrary size t values
that will wrap the value into a compile time type. So it will maintain the value at compile time. And now that we have that, we can write something that's very similar to the previous code snippet, which can be used for the test as runtime by using for args. So the body of our loop will be this generic lambda here that takes an n parameter as auto, and it will instantiate a buffer with n in the angle brackets, and then we'll do allocation, perform the test, and do the allocation. And this will be called using a variadic pack of sc_v values, where we specify the size of the buffer as a template parameter. So the way you read this is, for each integral constant over here, call this lambda and instantiate the buffer with the value inside the integral constant. So it's definitely not as pretty as the runtime version, but I think that the code is very clear and readable. We're iterating over a set of values and performing an action on them at compile time, but we're doing it without using template recursion or anything that requires you to write boilerplate code or introduce code duplication. With some additional abstractions, we can make it look even prettier. We could have a for values function that, given a type and a set of values, just calls this lambda on every value at compile time. And basically, if you see this function over here, it should be straightforward to wrap it in this nicer interface function. So let's run this code snippet, which is P04. And as you can see, it prints allocating and deallocating for every value inside the list of compile time SCV context variable instantiations. So this is pretty cool, but in the next code segment, we'll see how to do something even cooler by mixing static if and for args together. So in this code snippet, we'll see how powerful it can be to mix those two constructs together. Let's start with a reason to do that. Let's say that we want to iterate over types or manipulate types directly. So we need to somehow find a way to pass types as values. We can use the same principle as the Boolean and as the size t context variables for types. So we define a type underscore struct that takes a t parameter as a template parameter and exposes the type with an alias inside it. And then we can define a context variable for it called type, which will be of type underscore t. And you can think of this type t context variable as an integral constant used with types instead of values, if that makes sense. Then we'll provide an unwrap function that, given one of these type wrappers, it will return us the type stored inside. So now that we have this, we can use it with for args in order to instantiate various types and execute a test function with them, for example. So let's say that we have a tuple that contains a vector of int, vector of float, vector of double, and it's called buffers. And we want to resize all the buffers in one go. So in order to do that, we could use for args, and we could pass the types as the arguments of our for args function by using our type wrapper. So these are values that contain the information about the int, float, and double types. And they will be passed one by one inside this lambda here, which is basically the body of our compile time for loop. And t will be the type wrapper. So once we have t, we can unwrap it and get the inner type by using decl type and unwrap. Then we can compute the type of the vector by using unwrapped as the template parameter of the vector. And after that, we can use stdget to get the specific vector from the buffer list and call resize. So in this case, when we'll call resize all buffers, this function over here will be called one time with int, one time with float, one time with double, and this will, in the end, resize every vector inside buffer with a new size. So this was a pretty cool example. I think it's nice because it can be applied in various situations. Another thing that comes to mind right now is when you're writing a test and you want to parameterize the test over multiple types, like to try every combination of two lists of types, then you can simply nest two for args loops with the types and then run your test as the body of the for args. In the second example, we'll see how we can combine this functionality with static if. And in this particular implementation, we'll take a look at how we can call different functions depending on a type size threshold. So let's say that we have a function called init small object storage and a function called init big object storage, and we want to switch between them depending on the size of some type. So we'll use for args with a bunch of types over here. We have int, float, double, and a std array of double with 16 elements. And every type is going to be passed one by one inside the body of for args. T is going to be the wrapper, and wrapped is going to be the type that we get by looking at the insides of the wrapper. And then we can use static if inside for args in order to dispatch between those two functions depending on some compile time condition. In this case, what we want to check is if the size of the unwrapped type is less than 16. And in that case, we're going to call init small object storage. Otherwise, we're going to call init big object storage. This is really cool, as you can see, because we are basically writing imperative style code with a for each loop and an if, but we're dealing with compile time values. And those values in this case represents type. So this is nice. However, we have some annoying limitations that I will fix in the next code segments. Firstly, it's not possible to get the current iteration index, and that might be very useful if you're doing metaprogramming stuff where you want to assign an index to every value that you're iterating upon. It's also not possible to produce a result value, so you cannot do something like std accumulate but at compile time. And also there's no way of breaking and continue, which is something that's used often into imperative runtime loops. So in the next code segment, we're gonna fix all of these issues, and we'll do that by implementing our own iteration function that's called static for. This function, compared to for args, will add the following features, and those will be access to the iteration index, possibility to produce an output value, so some kind of accumulator, and an intuitive way of breaking and continuing inside the loop itself. One possible drawback is that the compile time will be slightly longer compared to the one by using for args, because we need to use recursion for this particular implementation. Before diving into the code behind static for, let's take a look at a motivating example. So this is quite artificial, but it will show you all the features at once. And in this case, we'll write a static for that will accept any number of compile time numerical values. Then it will accumulate the numbers and return the result at compile time. It will also print every even number and iteration. And it will immediately break when the special value -999 is encountered. So this is how we could write the above constraints using static for. And we need to know something first. Static for works by passing its current state as an argument to its own body over and over. And this allows us to basically inspect the state and ask it to give us back its current iteration as a compile time number, use it to set the next action to execute, which could be break or continue, and also use it to access the current accumulation value, which can be used for compile time computations. This is what it looks like. Print even and accumulate is a static for that, given a state and the current argument, executes all of this stuff over here. And the first thing we need to do is get the state and x as compile time context variables. For some reason this is required, even though it looks redundant, as we're just getting the type of state and reinstantiating it, because GCC wasn't happy with simply using state inside of constant expressions in the body. Also, what I'm going to do is going to assign a name to the predicates that we mentioned before. So we must break when x is equal to -999, and the iteration is even when the modulus between x and 2 equals 0. Now we can use static if to check on our breaking condition. So if we have to break, then we will return the special value provided by the state, that's break underscore. And this value here will instruct the compile time static for function to not continue with this next iteration. Otherwise, if the current iteration is even, then we print the iteration and the even number that we're iterating upon. And at the end, we return state continue, which instructs the static for implementation to keep going with the next value. And continue takes this parameter here, which is the next accumulation value. And to compute it, we'll get the current accumulation value at our current our current value to the accumulator, and wrap it into a compile time SZV context variable so that the type can retain the information about the value. So you should note that while the iteration and the accumulation is done at compile time, we can inject runtime side effects that will be inserted into the loop body, as we've seen with this stdc out call. So you can think of static for also as some sort of code generator. The above code is roughly equivalent to something like this runtime loop generator, where we have a function that takes an initial accumulation value and returns another function that, given some user-defined values, will iterate over every value, break if the current value is -999, otherwise print something if the value is even, and on every iteration it will increase this runtime accumulator here by the value of x and increment the current iteration. At the end of this inner function, it will return the final accumulation value. So as you can see, this is quite contrived because we have multiple returns here. So static for with a loop body is not going to immediately start running the loop body. We have 3 steps. The first one is calling static for with the body, which will return a wrapper for the body that can be called again multiple times. And this allows us to reuse the body with different accumulation values. That's why when we call static for with our body and then an initial accumulation value, we will get back another function that accepts a variadic number of arguments, and those arguments will be used to finally execute the loop body using the initial accumulation value. Lastly, we'll be able to call the function returned after binding the body and the initial accumulator, so after having this expression basically, with any number of variadic arguments, and this will fire the loop body on every argument, and it will eventually do some computation using the initial accumulation value. Let's have an example here. So we'll call print even and accumulate by binding 0 as the initial accumulation value, and we'll give a name to this bound function, which is PEAA from 0, which stands for print even and accumulate from 0. Then we will execute the loop and store the final result in R0. So we have an auto ctr0 here, which we will call the bound function with 5, 4, 15, and 35. And at the end, we will print the result to cout. And we also do the same with the runtime loop, which is the one that you've seen here. And we'll follow the same logic, bind 0 as the accumulation value, and then use 5, 4, 15, and 35. And then we'll print out the runtime result. And what we might want to check is that the return value from both of them is the same. So basically that our structure works both at compile time and runtime. So let's try and compile this code here. We get some warnings, but as you can see, the iteration for the even numbers is printed both in the compile time and runtime loop, and the final result is 59 for both of them. The difference is that this 59 here is stored inside an integral constant, so we could use it for further compile time computations. The next code segment will implement static for, and let's think of what we require to implement it. So we'll need a state class that keeps track of the current iteration, current accumulator, and the next action at compile time. And the iteration will be tracked by using an integral constant. The accumulator value will be provided by the user code by binding it, as you've seen in the previous example. And the next action will be implemented by using 2 empty tag structs. One will represent the break and one will represent the continue. We also need to iterate a compile time by keeping track of the previous state. So the only way we can do this is by using recursion. Let's implement the action classes first, which are pretty trivial. So I'm storing them inside this impl namespace and inside this action namespace, and I'm defining 2 empty structs called aContinue and aBreak, which will be just used as tags for the static for implementation to decide whether or not to continue or break. Then we can implement the state class. So the stored state has to be accessible compile time. Therefore, we need to use a lot of templates and constexpr. So the state struct itself will take an iteration value, the current accumulation value, and the next action as template parameters, and we will expose them to the user by constexpr methods which return an instance of those. So this is fine because the iteration will be an integral constant, so we're retaining the value information inside the type. The accumulator will be provided by the user, and the next action will just be either break or continue, which are different types. In order to allow the user to continue and break with a decent syntax that resembles the imperative one, we'll provide the continue underscore and break underscore functions, and they will optionally take a new accumulation value, and this is where the user can specify the logic to compute the next value from the current one. In order to make it easier to instantiate states, we'll have a make state implementation function that, given iteration, accumulation, and action, it will deduce the type for us and return a state instance with those defined arguments. And we also have an advanced state function that, given the previous state, a new accumulation value, and a new action, it will return a new state which has automatically incremented the iteration by 1, and it will set the next accumulation value and the next action as well. So this is something that helps us avoid forgetting to increment the iteration during the implementation of static for. So we can now provide a definition for the methods in state that you've seen. In the case of continue, what we want to do is simply advance the state, and the next action will obviously be continue. And in the case of break, what we want to do is advance the state with the new accumulation as we did for continue, but the next action will be break. So the only difference between the implementation of the break and continue methods on top of state is the next action that we're going to pass. And this type here will be detected by the static for implementation in order to see if we need to keep evaluating arguments or stop. The last and most complex part to implement is the static for function, and this will deal with iteration and accumulation. So let's take a look at the signature first. Static for will only take the body, because if you remember, it's going to be returning another function that will take the accumulation value first and then the variadic template. So we're basically manually carrying the function. And inside static for, we will define a step in our function that will deal with the recursion. Since it's not possible to write a recursive lambda, what we need to do is pass step to itself as a parameter, and in this case the parameter will be called self, and self will be used to recurse over and over. We'll also capture the body by forwarding it inside the step in our lambda. So step will take self, as I just mentioned. It will also take the current state, the current for each argument that's being evaluated, and the rest of the argument. This is done in two separate variables in order to use the first one with the body of the loop and then keep recursing on the rest of the pack. So inside the step, we'll start by computing the next state by executing body on the current state and the current x argument. So basically what we're saying here is, given the current state and the current argument, execute body on it and retrieve the next state. Now we need to check if this is the last iteration by using this constant expression here, which looks at the size of the parameter pack, of the remaining parameter pack, and if it's 0, then we know that this is the last iteration. We also need to check if the next action is a break, because we want to make sure that we immediately go out of the loop without computing any additional step. And in order to do that, we will look at the type of what the next state, the next action would return with this decal type expression here. And if the type is the same to impl action a break, so this is what it's checking, then we know we must break before we computed all of the arguments. Now it's time to deal with the recursion, and this is where static if will come in handy, because if we must break, or if this is the last iteration, we will return the next accumulation value and stop recursing. Otherwise, we will call self, which is actually step, because we're passing the function back to itself in order to allow recursion into a lambda, with the newly computed step and the rest of the argument back. So this is what it looks like. We have return static if, where we check if we must break or if this is the last iteration. And if that's the case, then we are on the final step. So we simply return the next accumulation value, which will be the final result that the user wants. Otherwise, we will call ourselves by passing self to this lambda here and calling it here. And we will do that by passing again ourselves, the next state, and the remaining set of parameters. So this was the inner step lambda. And in order to provide the user with a way of accessing it and starting the computation, we need to bind the accumulator value first, the initial accumulator value. And to do that, we return another lambda that moves step into itself, takes an initial accumulation value, and after binding it, it will return yet another function, which will take a variadic number of arguments, which will be used to start off the recursion. And these arguments here will be passed to the step using the accumulator value as the initial accumulation. Again, we use another return static if here, because if the initial pack provided by the user is 0, then we immediately want to return the accumulator because there are no parameters to be computed. Otherwise, we can create an initial state which starts from iteration 0, starts from the initial accumulation value accumulator, and by default uses the continue action as the first one. And after we have this initial state, we can finally call step with itself, the initial state, and all the user provided parameters. So that's it. It's quite complicated, but if you go slowly through the code and look at the comments, you should be able to figure out what's going on. Most of the complexity is due to the fact that we need to bind all those arguments to make static for as generic as possible. And also we want to make sure that we break whenever possible and whenever the user wants to. And also recursing with lambdas, as you can see, is a little bit contrived because we need to pass the lambda itself as one of these arguments. So that adds a little bit of complexity and syntactical overhead. So let's test our implementation by creating this static for here, which takes this body, and the body will simply print out the iteration, the value, and the current accumulator. And it will compute a new accumulator value by simply adding the current value to the previous one. And we'll always continue with the new accumulation value. Then we'll bind 0 as the initial accumulation value and call it with 10, 20, 30, and 40. So if we run this code here, I need to use my script. We'll see it print iteration 0, value 10, accumulator 0, then 20, then 30, then 40, which are the values. And the accumulator will be 0, 10, 30, and 60, and 100, which is the sum of 40, 30, 20, and 10. So this works as expected, and we can use the result value at compile time for further compile time computations. So for our last code segment, I want to take a look at the generated assembly and at existing production-ready solutions. So I have two test files in this repository, which I used to compare the generated assembly between a traditional handwritten compile time for loop and our static for. And basically, we didn't pay any extra cost from optimization level 1 for GSBOS+ and optimization level 2 for Clang. So we can say that static if and static for are effectively cost-free abstractions. You can fork and use the implementation shown here in your real project if you want to. Otherwise, you can use any of the following production-ready solutions. And obviously, I hope that if you have access to C++ 17, you'll use ifconstexpr, which is a lot cleaner than static if. For the first production-ready solution, I strongly suggest Luis Dion's Boost HANA, which hopefully needs no introduction. It's an extremely powerful metaprogramming library which uses type value encoding as one of these core principles, and it has extremely powerful constructs both for compile time, iteration, and branching. These are some of the very basic examples. So if you want to compute factorial of compile time, you could use HANA evil if, which is the counterpart of our static if. where you pass compile time condition here, and you call the base case and the recursive case here. And as you can see, instead of passing back the argument to the lambda, it is using a dummy underscore parameter, which is used to prevent instantiating the lambda in case this condition is false. We also have HANA for each, which given a tuple of values and a lambda, it will call the lambda with every value inside the tuple, which is something very similar to OR for each. Then another very cool library is Paul Foss II's fit modern function utility library, which can be used to replicate static ifs functionality. Here's an example that's provided by the author himself, where we have this decrement kind of, and we're passing a generic value here by reference, and this evil conditional function composition with an if underscore is what allows a compile time condition such as this one to be used for compile time branching. So this snippet here is one of the ways you could use fit to replicate static ifs functionality. And again, like the HANA implementation, this uses a dummy identity parameter here, which is whose job is to avoid instantiating the branch in case the predicate is false. Also, we can use fit compress and fit apply to replicate static force functionality. And in this case, compress with apply and the body of our for loop is equivalent to calling the body on every single argument. So I hope you find the talk interesting. Thank you for attending or watching it on YouTube, and feel free to contact me for any question.